So everything's set up.
Yeah, I think everything looks good. Arina's also on Zoom, so it's done. Thanks.
Oh, hi everyone in the room.
Oh, yeah, she can see that.
Yeah. All right. Thank you everyone for coming. It's probably going to be Vihan's last science seminar, but maybe if he graduates. Right, he's going to tell us about some work in the intersection of databases and graph theory. And
All right, thanks, Eber, for the introduction. Yeah, so this is a talk about counting 4 cycles in the dynamic model. So yeah, this is joint work with Zephyr, and this is accepted to Paul's. Okay, so let's start with the question of subgraph counting, right? So you're given a graph G and a pattern graph H, and you want to count the number of copies of H and G, right? And in our case, we're interested in counting 4 cycles. And subgraph counting has many applications in social network analysis, telecommunication networks, etc. I'm going to show you an application in database theory. So you have these 2 binary relations here, A and B. And the way, I mean, this relation is just, you should think of it as a bipartite graph. And if one is present, there's an issue. So the first relation is an L1 and L2, the second one is on L2 and L3. And one operation database people are really interested in is joins, right? So okay. Yeah, so the join of these 2 tables would be this table here. And how I think about it is, again, in terms of graphs, you just want to merge these 2 graphs on L2. Right? So you can just do that. And now every element of the join corresponds to a 2 path in the graph. Right? So the number of 2 paths is the join size. Okay. So let's talk about 4 cycles. So over here you have like 4 binary relations, A, B, C, and D. And they're over 4 sort of layers, L1, L2, L3, and L4. And you want to consider the join of all of them. And so the size of the join here will be the number of 4 cycles. But there'll be like a special kind of 4 cycle, which I call layered 4 cycles. So for example, in this graph, this is a layered 4 cycle. So you need to have 1 vertex in each layer, right? And this is not a layered 4 cycle. Yeah, so this is, we'll be interested in layered 4 cycles. And throughout the talk, we'll just focus on layered graphs, right? And I'll tell you this why. It turns out it's equivalent to general graphs. But okay, in our case, in the case of 4 cycles. But okay. All right. So let's talk about the dynamic setting. In the dynamic setting, edges can be inserted or deleted. And you want to solve the problem after every update, right? And the goal is to minimize the total update time. So let's do an example here. Like you have these edge insertions, then you could also get deletions. And after every update, you want to output the total number of 4 cycles in the graph. Okay. So what do we know about subgraph counting in the dynamic model? So let's start with triangle counting. So triangle counting has an upper bound of square root m. This is given by Kara et al. And m here is the number of edges. Okay, so we know an upper bound of square root m, and we also know a lower bound of roughly square root m, right? So this is a conditional lower bound, like conditioned on OMV. And yeah, so square root m is kind of the right answer for counting triangles. Okay, good. But what about 4 cycles? Do we know tight bounds there as well? And turns out we don't. So the bounds over here are not very well understood. So you have this upper bound. Sorry. I just want to say one more thing, which is we're interested in counting 4 cycles because it's sort of the smallest graph where we don't understand the right bounds of it. Like for triangles, we know it. For 3 parts, like parts of length 3, we know it. But for already for 4 cycles, we don't know what the right bounds are. Yeah, so there is an upper bound of n to the 2/3 by Hanover et al. And the lower bound still stands at square root m, right? So the same lower bound as the triangle case holds here as well. So the question is, okay, like, what is the right answer over here, right? Between 2/3 and 1/2. Okay. So the techniques that were used by Hanover et al. Were a natural generalization of the triangle counting ideas, right? So they use some sort of a high-low decomposition, and when you look at that algorithm, it feels very natural that, oh, okay, this, I mean, if n to the half was the right answer in triangles, maybe this is the right answer here as well. So we believe that n to the 2/3 was the correct answer, and we tried proving a lower bound. So we wanted to match the n to the 2/3 lower bound. But we tried and we failed, right? So what do you do when you can't improve the lower bound? You prove an improved upper bound, right? So that's what we do. So we give an upper bound of n to the 2/3 minus epsilon for the update. Yeah.
Are there lower bounds for the case that you were just looking at the graph, not the graph?
Uh-huh. So in the static case, we know that triangle counting, so okay, both problems, triangle and 4 cycle counting can be solved in n to the omega. They also can be solved in terms of number of edges as well. But you have conditional lower bounds there, so you can't improve both the cases. Yeah. Okay. But okay, yeah. So yeah, I'm sorry, please stop me and ask me for questions. Maybe I'm going too fast. Yeah. Okay, so what do we get? We get a slightly improved update time, right? So this epsilon is like a small constant. And this is for counting layered 4 cycles in 4 layered graphs. Right? And what is this epsilon? It's actually dependent on the matrix multiplication exponent omega. Right? So with the current best bound on omega, you get epsilon is roughly 0.01. So you make this 0.66 or 0.65. And with the optimal bounds on omega, we get epsilon is 1/24. So we get like a significant improvement in the second limit. So good. And we also show that this problem is equivalent in layered and general graphs, right? So we can just focus on layered graphs. So, any questions? Yeah.
So you said conjecture, your conjecture.
Yeah, so before we got this algorithm, we thought m to the 2/3 was the correct answer. And maybe for combinatorial algorithms, it might be the right bound. But we show that actually, if you use fast matrix multiplication, like if you're not constrained, then you can improve the m to the 2/3 bound. Yeah, so before solving the problem, we thought m to the 2/3, but then we solved it faster than that. So then, okay, yeah.
Only for layer, but you said layer 4 cycle.
Yeah. So even for general graphs, counting 4 cycles, you can do it faster than m to the 2/3. Yeah. Good. Okay. All right. So let's move on. So let me just tell you about the problem again, and we'll reduce it to a slightly different version. So you should think of A, B, C, and D over here as native fields, right? That contain these edges of the bipartite graph. So we can have insertions or deletions in any of these layers. Then after each update, you want to output the total number of 4 cycles. Okay, so how do you output the total number of 4 cycles? If I know the previous answer already, all I need to calculate is the number of 4 cycles that is going through this edge, right, currently. And then I can add or subtract it to the previous answer. Okay, good. So I just want to focus on counting the number of 4 cycles that go through this edge. But what are the number of 4 cycles that go through this edge? The number of 3 paths between these two endpoints, right, that go through A, B, and C. So I will just focus on the number of 3 paths between these two vertices. And also, without loss of generality, we can assume that the update with the query is always in B. Right? Because we can run 4 copies of the algorithm. So whenever there's an update in A, you ask the A algorithm, oh, what is the answer? Right? So we'll always assume queries are in B. So the reduced problem now looks like this. We can have insertions and deletions in A, B, and C. And for the talk, we'll just focus on insertions. Let's just think insertions are happening. And the queries will be in D. And what is a query? A query is like I give you U and V and tell me the number of 3 paths between you. So we're going to solve this problem equivalent to the original problem. Yeah, everyone go to this? Okay. And again, each operation should be completed within the update time. So the update and the query both should be done in the update time. Okay. Good. So let's start with a simple algorithm. And now comes the part where I'll show you a couple of algorithms. So I want you to try and answer these questions. So let's see if we can figure these things out. So question 1, can we get an algorithm with update time ordered? Right? So the question is, I'm going to give you U and I'm going to give you V. And I'm asking you the number of 3 paths between U and V, and you have to answer according to order and time. Right? And you're allowed to store some data structures if you want to answer this very quickly. So does anyone see how to do it in order and time? I'll give you a minute to think. You want to say something, Rani?
You guys see my work.
Yeah, she's seen this already, but okay, you can still say. Or does anyone else like want to answer? If not, I'll ask that Rani to answer. Okay.
We can try and store the number of 2 parts we like L1 and L3. And not whether even these to get all the neighbors of V and see how that's again.
Exactly right. Yeah. So what I will do is during the query, I can iterate over the neighbors of V. And since I know there are at most n neighbors, I can do this. But now I've run out of my query time. So now all the operations I want should be in constant time. So I'm going to ask all these vertices, these 3 vertices, how many paths do you have? How many 2 paths do you have to view? And they'll tell me how many 2 paths they have. And I'll be. Right? So all you need to store is this data structure that tells you the number of 2 paths between this layer and this layer. Make sense? Right? I can over neighbors and then ask for 2 paths. And why can we store these 2 paths? Because if there is an update here, then I can just iterate over all my neighbors in L1 and update the number of 2 paths between this guy and those guys in L1. I can just increment the paths by 1, right? Because all the new 2 paths are only through this edge. So either they look like that or they look like that. Right? So I can store number of 2 paths between L1 and L3. I can also store number of 2 paths between L2 and L3 in order. Does this make sense? And we can spend some time here because like all the other ideas will be based on something like this. So I just want to make sure everyone answers. Okay. So this data structure you store is a bunch of 2 paths between pairs of vertices, and it's of something of size order n squared, but we don't care about size at all. We only care that this is going to give us quick access time. So while we're doing the queries, we can access this very quickly. Right? Okay. I did over neighbors, store 2 paths. That's the idea. Yeah.
You update like your vertices.
Yeah. So maybe just think of all these layers. Let's say have vertices, something like that. I want to store the number of paths between this guy and this guy, right? And I don't want to compute it all together. I just want that, oh, this is the new update, I'm going to update it. So you should think that I already have all the values, then this new item values. Now how do I update it? So only two paths that include this edge will be updated. So all the paths will be like this guy and one vertex from him. Those will form two. There are only order and two paths that can change. Okay, good. So let's now try to get the dependence in terms of M. Right? This is what we saw in the introduction. You can get dependence in terms of M. So what can we do? So Hannah et al. Gave an algorithm with update time and to the two. Right? And how do we get this sort of dependence on them? What we can do is what they did was they used the high-low decomposition. That was the main idea. So you decompose the vertices into high and low based on this threshold m to the 1 over 3. Right? So you pick some arbitrary threshold, figure out that m to the 1 over 3 is the right one. And okay, what is the advantage of the decomposition? So on a high level, what is going to happen is that the number of high degree vertices is going to become small, right? Because they have a high degree. And the low degree vertices have a few number of neighbors. So we're going to exploit these two facts. We're going to store data structures where for low degree vertices, we can iterate over their neighbors. So we're fine. But for high degree vertices, we can store data structures because the number of them is okay. And let me show you what I mean with this. So for example, we can store this data structure. And now let me tell you what this notation means. AHL just means I'm looking at high vertices in L1 and low vertices in L2, right? And again, say LL is low and low, and same for C as well. Okay. So I can store the number of free paths between any vertex in the first layer and any vertex in the last layer that go through lower degree vertices. And does anyone see why we can do this? I think in m to the 2 over 3 time, why we can store this? I think, yeah. And I've put the threshold here between high and low if you just want to, look at it. So why can you store such a data structure in this much time? M to the 2 over 3 times.
So because they are only like 10 raised to 1 or 3 pairs of inside.
Good, exactly. Yeah. So whenever I get an update, if the update is here, then there are only m to the 1 over 3 neighbors on each side. So I can just go with all pairs of neighbors and update the number of free paths. Right? And even if the update is here, I can go with the neighbors of neighbors. Right? So that's again to the 1 over 3 and then to the 1 over 3. Right? So I'm good and to the 2 over 3 times. Okay. Good. All right. So we can also store two paths for high degree vertices. And star over here just means I'm not making any assumption. The whole layer is okay. Right. So between these guys and these guys here, I can store the number of two paths between all pairs. And why can I do this? Again, this is because the number of high degree vertices is small. So whenever there's an update, I just have to go over my neighbors in this portion. Now you might say, okay, the number of neighbors in this portion might be hard to find because if I take the adjacency list or the adjacency matrix, I'm in trouble. But what I can do is I have a list of high degree vertices stored, right? So I can just iterate over the high degree vertices, check if this edge exists, and if it does, I'm going to increment the number of two paths. Yeah. Okay. So the two key ideas are again that one is that you can store paths through low degree vertices, and you can store paths where endpoints are high degree. Right? Yeah.
And can be increasing, look, say, when it dynamically changes threshold width.
Yeah. So you should think of right now what's happening is we currently have m edges. We're going to go up to 2m edges, and things are happening in the middle here. But what I'm not going to assume is like we're not going to worry about m changing, because what I can do is just run multiple copies of the algorithm, and at powers of 2, you can do some changes. Again, for the vertices that belong to different classes, they might shift, but we're not going to worry about that because you can do something like this for that as well. Okay, good. All right. So how do you answer queries using these stored data structures, right? So let's say, for example, if both the guys are low, I can just iterate over their neighbors. And for all pairs, I can check if there is an edge, directly compute the number of tree paths. Very simple. So we don't need any data structures when both vertices are in. Okay. Good. Let me give you another example where we use a data structure, which is, let's say for high degree vertices, how do I figure out the number of paths between the elements? So one thing we can do is we can use the data structure we stored that goes through low degree vertices. So this is already in order one time giving me the number of paths, right? Because we've stored. But we're still missing paths that go through high degree vertices, right? Like this is an LL path. We're still missing HL, LH, and HH paths, right? So we still need to figure out how to compute them. Okay. Yeah, let me just pause here for a minute and ask, like, are people following? Because I think there's like a lot of things to keep track of. So again, at any point, I think if you don't follow this, let me know. Okay. All right. So this is easy because we've stored this data structure. What we can do for the high degree paths is I can iterate over all my high degree neighbors, right? And then use the number of stored two paths. So we stored the number of two paths between all of these guys and all of these guys. Okay? So I can just iterate over all my high degree neighbors and then just use these stored paths. Okay. And yeah, so the data structure is this one. Okay. So, okay, let me ask you another simple question. So, what about HL paths, right? So we took care of LL paths. Now this is going to take care of paths that are anything here, so H or L here and H here. And what do we do for paths that go over high degree here and low degree here? Does the question make sense?
You're still running just with doing BC.
Yeah. Yeah, things are symmetric, right? So if we can find things from this side, we can also do the same thing from that side and store these paths. Right? And if you're worried about overcounting, because it looks like if you do the same thing from the other side, we're going to overcount these HH paths. But we can just store the structures separately just for HL and LH and HH, and then it'll be good. Yeah, so yeah, you don't have to worry about overcounting. Part does not seem convinced. Yeah, if you just do HL and HH, the argument is the same, that's why they did start. Yeah. Okay. Good. So, do we believe that this algorithm works in M to the 2 over 3 time? I've not shown you all cases, but I think these are the kind of ideas basically that like you can just do all the cases by yourself, and you can see that this is going to work in two or three times. Right. So the question is, okay, how do you get this minus epsilon? Right. Because yes, sorry. So yeah. So they did 4 cycles and they also did other 4 vertex subgraphs, but I'm not going to talk about that. But yeah, they got a bound of 2 or 3 for them. Yeah, that's how they did it. Yeah, good. So yeah, how do you get this minus epsilon? Because yeah, yes.
So why does it one half instead of 2/3? Easy.
Yeah, because the thing is, when you do the same reduction for counting triangles, now instead of looking at 3 parts, you're looking at 2 parts. And 2 parts are actually much easier to work with than 3 parts. You don't have to store all these complicated data structures. So the threshold they pick is like square root n. And yeah, like just because handling 2 parts is much easier, they get square root n and stuff. And
Because of that in different things.
yeah, yeah, the ideas are the same, but again, like iterating over high degree vertices will take square root n time, and then you just have now you're just working with 2 parts, so it's easier to get these data structures quickly. Okay. Yeah. So how do we get this update back, right? And let me give you like a sort of example, which is like a barrier. So for example, if I just have these low degree vertices, okay, and I want you to tell me the number of paths between, how are you going to do it? You can't iterate over both of their neighbors because that's what we did for 2/3 time. But now in less than 2/3 time, you cannot iterate over their neighbors. Right? Good. What you also cannot do, and this is the problematic thing, is that you cannot store data structures for low degree vertices directly. Why? Because when there is an update, a lot of these things might change because the number of low degree vertices are at least m to the 2/3. I would have to update all of these data structures, like for two parts, right? So, and when you add an edge, many of them are going to change. So it's not like, yeah. So, for example, if this vertex has many edges to L, like constant fraction of L, then those many two paths are going to change. So there's no data structure you can store directly that tells you the number of two paths, right? So it's hard to answer these LL queries, for example. Even for other cases, there are some difficulties, but this is one we should maybe keep in mind. Okay. And now we're going to see how do you fix this. So what is the idea, right? Okay. Yeah, everyone on board? Good. So what is the idea? So let me ask this a good question. Okay, what if you had m to the 2/3 minus epsilon in this? Can we answer queries in that much time as well? And we're like, okay, of course. This is like linear in the number of edges. So of course we can do this. But what I need to ask is something slightly different. Right? So what if A and C are fixed with order and limits? So I'm telling you no updates will come in S. Okay. And B only has m to the 2/3 minus epsilon. Now, if I ask you between this vertex and this vertex, tell me the number of three paths. Can you do it in this much time? Does anyone see how to do it? Right, so for now, everything is static. These guys are fixed. I'm also fixing a very small number of edges here. And I'm asking you between the first vertex here and the second vertex here, for example, how many three paths are there? Can I calculate them quickly? Yeah. Perfect. Exactly, right? So I'm going to call this lazy evaluation. I'm going to go over each edge in V and check if it forms a three path. I can check if it forms a three path in constant time, right? For example, this edge. Does it form a three path with the first guy? No, I mean, this edge does not exist, so it is not. So I just have to check both sides because these vertices, the query vertices are fixed. So I just have to check if this edge has an edge here or has an edge and has an edge. Both edges exist, that's going to contribute one to the number of three paths. I go over all of them and sum it up. Yeah. Makes sense? This is like the laziest thing you could do. No data structures, nothing, just store it. Like just do everything during query time. Okay, so we're going to use this idea in the following way. So let's say these are all the updates I'm going to get in B. Okay, A and C are fixed. So initially B you should think of as empty, and I'm going to add edges to B. So these are the edges I'm going to add to B. And I'm going to break them up into chunks of size m to the 2/3 minus. Okay. And okay, I'm currently here, right? No edges have been inserted. Once the first chunk is inserted, like, or while it is being inserted, if any query comes, I can answer it by lazy evaluation, right? Because the total number of edges in B is small. Yeah. Okay, so the next round you can do the same thing as well. But you can't keep doing this because eventually you'll gather too many chunks, right? So in parallel, we're going to do something. So when chunk 2 is being inserted, right, you answer queries for chunk 1 and 2 using lazy evaluation. But in parallel, I'm going to compute some data structures for chunk. And now you can probably see where we're going to use fast matrix multiplication, right? So when I'm computing these data structures, I have the whole chunk with me. So now I can maybe do things faster. Okay, so good. Again, and then when this moves forward, during chunk 3, we're computing data structures for chunk 3. But the queries you're answering. So you're doing lazy evaluation for 2 and 3, but for 1, you're going to use data structures that you've already stored. Right? So lazy evaluation is always on the current chunk and the one before it, right? And for all the guys before it, you've already computed data structures. So you're going to use those to answer the queries for them. Right? This high level idea makes sense? Okay. Yeah, if not, we'll see the details now. But hopefully this makes sense, right? Just use lazy evaluation for the current chunks. It's the previous one, compute some data structures, use them to answer queries. Okay. All right. So this is the sort of warm-up algorithm where A and C are fixed, right? And we will drop this assumption. So I'm going to talk about a couple of assumptions now. We will drop this assumption in the final algorithm. The second sort of important assumption that I'm not going to talk much about is that the minimum degree is something like this, right? M to the 1 over 3 minus 2 or so. And the reason we can assume this is we have this other algorithm that we can come up with that can handle these low degree vertices. Yeah. And what I mean by handle is you can answer queries for them. You can also calculate paths through them. And what this will imply is that the number of vertices in each layer is roughly m to the 2 over 3. Right? And this is like a very important assumption. So in your head, you can think that instead of every layer having n vertices, they now have roughly m to the 2 over 3 vertices. Right? And epsilon, again, in your heads, keep it as 0.001. Right? Okay. Good. Yeah, makes sense. Just every layer is small. Okay. And finally, rectangular matrix multiplication is as fast as reading the input. And this is easy. I'm going to leave it as an exercise. Right? But okay, joking aside, I mean, of course it's not, right? But I'm just going to use this for this, right? And I see Sriram not happy, but yeah, just for simplicity, we're going to assume this. We don't need this. So we can use the bounds on rectangular matrix multiplication. Get something. If you use optimal bounds, you'll get better constants. That's it. Okay. Yeah. So let's now see how we can do these things. Okay. Good. So, all right. So just like the algorithm of previous work, we're going to use some partitioning as well. So the first and the last layer, we're going to partition them into high, medium, and low degree vertices. And the thresholds are roughly near 1 over 3 and 2 over 3. Again, you don't have to worry about these plus minus epsilon like too much, but they're important and they'll show up in the calculations. But for intuition, you want n to the 1 over 3 and n to the 2 over 3. Okay. Good. So let's try to see how we can answer some queries. Right? And, okay. Oops. Yes. So the goal is, let me remind you, and I'm going to ask you a question. So you want to compute these data structures for the previous chunk in the time the next chunk is inserted, right? So earlier what we were doing is every time there was an update, we were going and updating the data structures. But now we have the whole chunk with us. So we want to create the data structures in time it takes to insert a chunk. So this is m to the 2 over 3 minus epsilon squared. Right? Because this is the chunk size and this is the time allowed. And the queries need to be answered in this much time. Right? So you compute data structures in this much time. You answer queries still in this much time. Right? And don't worry about the current chunks. We're just going to use lazy evaluation for that. Okay. So let's start. We need the number of 3 paths between U and V going through BI. Right? And for now, I'm assuming this case is LM. So U is a low degree vertex and V is a low degree vertex. How do we answer queries for this? Okay, this is okay, not an easy question, but does anyone see any simple way to do it, or do you see like, okay, this is going to be hard because of something? But at least why the previous idea does not work. Okay, let me just show you why the previous idea does not work. Is because I think over pairs of vertices is going to take too much time. Right? This is again the sort of issue we had earlier when we were saying that okay, this algorithm going down to m to the 2 or 3 minus epsilon is going to be a problem. Right? You cannot do this. So we're somehow going to use fast matrix multiplication. Right? So what we're going to do is iterate over neighbors of this vertex and then try to use the number of stored 2 paths. Right? So this is the data structure we're sort of aiming for. Good. Okay. So let's see what we're going to do for the stored 2 paths. If we if we naively try to store this data structure like we did earlier on the fly, this is going to be a problem, right? Because the neighbors of this guy are 2 minus. You cannot store this on the fly. Can we use fast matrix multiplication? Okay, let's look at the dimensions of the matrices we have. So this matrix over here, Vihan, is of dimension n to the 2 over 3 minus epsilon. Right? Why? Because this is just the chunk size. So there are n to the 2 over 3 minus epsilon edges here inside this. So if a vertex is degree 0, we just ignore it. Right? So the matrix Bi, sort of what we have, is going to be just of this dimension. Okay. What about the matrix A? Okay, the second part is going to be the same, but the first part is going to be all low degree vertices. And they're roughly n to the 2. Okay. And this is because of the assumption we had that each layer has size n to the 2. Okay, plus 2 epsilon. But does anyone see a problem with like doing this computation in n to the 4 over 3 minus 2 epsilon times? Like even fast matrix multiplication is not going to work here. Because, okay, what is the dimension of this matrix? It's 4 over 3 plus something, right? And we want minus something. So this matrix is already too big to even read. Good. Okay. So, okay. So let me just recap. What we want to do is store this data structure that between L1 and L3, I get the number of 2 parts, right? But I'm not able to store the 2 parts on the fly. And I'm also not able to use fast matrix multiplication to store the number of 2 parts. Right? Okay, so what are we going to do? And okay, so notice that this partition that we had was only for the first and last layers. Right? We didn't do it for the middle layers. So now let's do the partition for the middle layers. Right? And I'm just going to use separate word like letters for this, but this just means high and low. Like this is high and this is low. And we're going to pick some different threshold. Right? Now we just want like 2 classes here, and we just want to figure out the number of paths through one of them through the other one, just like we did in the algorithm of previous work. Okay. So the threshold is roughly at n to the 1 over 3, but it's minus some epsilon prime. You don't have to worry about what the exact value is. It's some small constant times epsilon. But yeah, the threshold is at roughly n to the 1 over 3, and the max is n to the 2 over 3 because that is the chunk size. Yeah. Okay. So I'm going to show you. Okay. So yeah, let's look at the first data structure, which is through the dense vertex. Okay. And this is the data structure we want. So you have low degree vertices here, and you have dense vertices in the middle. And you want the number of paths to be like a vertex here and a vertex here. And now this is going to be easy to do, right? Because the number of dense vertices is small. Yeah, you don't have to worry about exactly what number this is. But the number of dense vertices is going to be small, right? Because they have a minimum degree. So the number of them is going to be small. And so that is enough for us to do fast matrix multiplication. Like, so this matrix times this matrix is going to give us the number of 2 parts. Right? Okay. Yeah. So this is going to take time n to the 1 plus something, which is much smaller than 4 over. Okay. Good. Are there any questions here? Okay, good. So, yeah, all you need to understand here is just because the dense vertices are a lower number, you can do this matrix multiplication and store the number of paths, right? But when we go to the sparse case, right, we want to store again the number of two paths. But now this picture is a bit misleading. Like this is not going to be this small. The number of sparse vertices is almost the size of the layer, right? So this matrix multiplication is still going to take as much time as it did initially. So we can't do fast matrix multiplication. So does anyone see a way to fix this? I guess it's probably going to be the last question I ask you. And it has something to do with the matrices being sparse. Okay. So since the matrices are sparse, a lot of these pairs are actually going to be zero. There'll be no two paths between them. Right? So we don't have to spend any time figuring out the number of two paths between them. So all we have to do is go over each low vertex, go over their neighbors and their neighbors. Since this is a low degree vertex and this is also a low degree vertex, the number of neighbors are going to be really small. Right? So in the high degree case, you could do this because the number of high degree vertices is small. Over here, the number of neighbors is small. So you just go over the neighbors and update the number of two paths. Right? And this computation is going to take time. Yeah, like, and this is why we needed epsilon trying to be slightly different than epsilon. It's like a small thing. But it's n to the 4/3 plus this thing here, which is within the update. Okay. Good. So let's just see how we can answer the queries now. Like we've stored both of these data structures. So we can answer, like look at like the two paths that go through the both dense vertices, like sparse and star. And also if you want DS paths, you can look from the other side. The same trick as before. Right. So now we've done all four kinds of paths, and so we're done basically. We can answer the queries for Lolo. Does this make sense? Okay. Yeah, and this was one of the hard cases. And okay, now let me just tell you one more thing here. Is we're doing this for all the chunks, right? So just remember the previous picture where for the current chunks, we're doing lazy evaluation, but for everyone before that, we're storing data structures, right? But if we keep just storing data structures, then let's say if I have a query, I'm going to go ask chunk one, oh, what's the number of paths in chunk one, what's the number of paths in chunk two? And if I do this naively, I'm going to get a factor I in the query time. Right? So we just need to do a simple thing, which is aggregate the data structures. Right? So if I've computed something for chunk 1 to chunk 10, every time there's a new chunk, you just aggregate the number of paths together. Right? So for all chunks up to I, look at the aggregated thing for I minus 1, and then add the current thing to it. And note this adding thing works only because A is fixed. Right? Once A is not fixed, I can't just add. Right? Because what I've done is partition B into a bunch of different chunks. So what is the number of two parts of the first one to the second one? And since A does not change, I can do this. Make sense?
Big last thing, big function.
Okay, yeah.
We have just in the first layer fix.
Yeah.
Third layer fix.
Yeah.
You assume that we insert just in the middle.
Yes. Yeah.
We have chunk. The data structure.
Yeah.
4/3.
Okay.
We cannot sort of one query. Is it replicating or?
Okay. Let me just go back to the picture. Might be a bit- Yeah. So let's just look at what's happening in the big picture, right? So what I'm going to do always for let me go here.
Okay, it's the query now.
Yeah. So okay. So now the query is again, I'll give you U and V and tell me the number of 3 paths between them, right? So I look at the current 2 chunks and answer queries for them quickly using lazy evaluation. That makes sense? Right? The number of edges is small, so that part I can handle easily. But maybe this old part is very big, right? There are like order n edges in the old part. But the thing is, answering queries for them can still be done in 2 over 3 minus epsilon time. The only this part, computing the data structures part, this is where I take 4 over 3 time roughly.
Yeah, so how is it? It's time to go forward.
Uh-huh. Oh, good. Okay. So the way these M to the 4 third works is like while inserting chunk 3, for example, we're computing data structures for chunk 2. So you're doing this in parallel, right? So how much time does it take to insert this whole chunk? Of like roughly 4 over M to the 4 over 3 time, right? And while that insertion is going on, I'm going to spread this computation out over the updates. So the worst case update time is still M to the 2 over 3 minus epsilon. So since the total time is M to the 4 over 3 minus 2 epsilon, and I have some computation to do, which is done in time at most M to the 4 over 3 minus 2 epsilon, I'm going to use M to the 2 over 3 minus epsilon time per update. And I'm going to spread the computation over all those updates. Makes sense? Okay. Yeah, so the big picture is just, yeah, this picture here. Lazy evaluation for the current chunks, that will give you quick query time. And you've already stored data structures for the previous chunks, and you've aggregated them. So answering queries, like, I mean, so the query thing will be a sum of 2 things, right? The answer you get from here and the answer you get from here. Right? So the paths through the current chunks plus the number of paths through the old chunks. The number of old chunks, the data structure, using the data structure, you can answer the query in M to the 2 over 3 minus epsilon time.
It's only for one query in the first thing.
Yeah. Like you can do like, okay, you can ask me another query after that. I'm going to just take again M to the 2 over 3 minus epsilon time to answer that query. So like for each query you ask me, you can keep asking me queries, that's totally fine. But for each of them, I'm just going to use M to the 2 over 3 minus epsilon time. Yeah, we have time, so you can yeah, ask, like, yeah, does this make sense or still not exactly? Okay. Okay, so all right. Like after the talk, I'll just draw something and then show you. Okay. But all right. So let me just go back. Let me just tell you a little bit about the final algorithm, right? Then how do you drop this assumption? So yeah, I'm just going to skip one case because that is very similar to the algorithm of previous work. No fast matrix multiplication, so no fun. Okay. So okay, we just want to generalize this now. So you want to drop this assumption that A and C are fixed. Right? And as we saw right now that we cannot do this aggregation. This is going to be a problem for us. And the idea is something like A and B both are changing. So if I do something for A1, B1, and then A2, B2, I also have to figure out something for A1 and B2, right? So there can be paths that go through A1 and B2 as well, right? So this idea of chunks and lazy evaluation doesn't work, right? Or doesn't. Maybe we can do something similar. And the idea is this. So if I tell you that I just am interested in M to the 1 minus delta edges over which I want to solve the problem, I can easily do this by running the algorithm of previous work, right? If the number of edges I'm interested in is like M to the 1 minus delta, again, delta is like some epsilon times some constant. So then I can just run the algorithm of previous work and I'm done. Okay. And so similar to the chunks, we're going to consider phases of size n to the 1 minus delta and run the algorithm of previous work on it. And in parallel, we're going to compute data structures using fast matrix multiplication. Again, the idea is the same as before. Right, so the picture, again, now maybe, yeah, like maybe if this makes sense, hopefully. But let's say you already have images, and between all pairs of vertices, you've already computed some paths. Okay. What I'm going to do now is for the incoming, the rest of the edges, I'm going to partition them into blocks of this size and the 1 minus delta. And again, for over here, you have already stored paths. And for this guy, I can run the algorithm of previous work because the number of edges is small. Okay. And note that over here, we only focus on 3 paths that are either completely in the old phase or completely in the new phase. Right? So right now, if someone asks me a query at this point, what am I going to do? I'm going to look at this block and run the algorithm of this to get the number of paths. For this guy, I just have all the number of paths stored. So I'm just going to ask it, and then I can sum those up. Right? If I'm just interested in these kinds of paths. Does this make sense? Right? Again, this is just a partition of the edges. So I can calculate something that goes through this and goes through this. And note that there can be some paths that have some edges here and some edges here. We don't worry about them for now. But this sort of makes sense. Okay. And so again, just like before, you can keep doing this, but in parallel, you want to compute data structures, right? So again, during phase 2, you compute data structures for phase 1, and you just compute the number of paths between all pairs, and you will use fast matrix multiplication for this. Okay. And so then you can absorb this into the old phase and then keep going. Okay. Yeah, and how do we compute this? You're just using fast matrix multiplication, and you know the layer sizes are this one. So the complexity will be just this thing times omega, right? And yeah, we're almost done. I just wanted to highlight one cool thing, which I don't really understand well, which is okay. What we're going to do is this is the amount of time it's going to take for us to do the fast matrix multiplication between these two matrices, right? And we're going to spread the computation over the time this, like the whole chunk is inserted, like the whole phase is inserted. Right? So that's this thing times this thing. And if you just do this calculation, I'm not going to make you do it, you're going to get that omega is less than 2.5, which to me is surprising that like the original fast matrix multiplication does not give me a faster algorithm if I use it as a black box. Only fast matrix multiplication algorithms that are faster than 2.5 will make my algorithm run faster than n to the 2 over 3 times, which is surprising. But okay. And yeah, if you just use omega is equal to 2 here, you'll get that epsilon will be 1. So this is where we get our constant. But okay. All right. So what we've done is we've taken care of paths that are completely in the old phase, and we've taken care of paths that are completely in the new phase. Right, but the main challenge is figuring out these paths that have some edges in the old phase and some edges in the new phase. Right, and the only thing I want to say here is if you look at these kinds of paths where A and C are on the old phase and B is in the new phase, this is exactly the warm-up algorithm. So A and C are fixed. The old phase edges are fixed, and the new phase edges are sort of income. And this is where we use the warm-up algorithm as a subroutine in our main algorithm. And you still have to worry about all of the other cases that I'm not going to talk about. Okay. So, all right, let me just end with some open problems now. Okay. So the first one is that, of course, there's a huge gap between the upper and lower bounds now, right? We believed m to the 2 over 3 was the right answer. We broke that belief. So now this is wide open that, okay, what is happening? Okay. Also, the reason we got interested in this is because not much was known for even small, like counting small, like pattern graphs. And so, for example, what about other full-vertex subgraphs, right? Or even maybe even larger graphs. And yeah, like what about combinatorial algorithms? And some people don't like this. I'm pretty sure Robert and we don't like it. But yeah, if we consider combinatorial algorithms that don't allow fast matrix multiplication, it, can we get that m to the 2/3 is the correct answer for those class of algorithms? And finally, the way I stated the problem, I broke it down into queries and updates. And so can we get a trade-off between them? Because for now, both the query and update time are the same. But okay, this is all I have for you today. Thank you so much for listening. Oops. Just going to, okay.
Questions would be.
I have a question.
Yeah.
So what about maybe approximate counting? Does it even make sense? Like maybe you don't want the exact, but I don't know, some.
Right, right. Yeah, approximate counting does make sense. I don't know about the literature on it, but over here we were just focused on deterministic algorithms, exact count.
Mm-hmm. Okay.
Yeah, like even things for are not known here. But yeah,
Okay.
I'm sure, yeah, approximate counting also makes sense.
Um, okay. So another question I have,
Yeah.
what about the lower, like the lower bound?
Mhm.
Like what do you expect it to be? Like can it, so it's known to be something like m to the 1/2 plus epsilon, right? From triangles or just m to the
Yeah, 1/2 minus epsilon from there.
Ah,
Yeah. Yeah, I don't know. Actually, yeah, I have no idea. I feel
so
like,
how do they do it? Like what reductions or
yeah,
how do they think about it?
yeah. So I think it's the lower bound is actually very simple. The way to think about it is just think of a 3-layered graph, right? And I'm going to use OMV to give you a lower bound, right? And I'm going to use this version called OUMV, where I give you a vector u and I give you a vector v, and multiplying u times the matrix A times v is going to take n square time, right? And if you want to think in terms of m, it's going to take m time if the matrix is m by root m. And just I'm going to place the matrix A between layers 1 and 2, the vector u between 1 and 3 that goes from the back, and the vector v between 2 and 3. So just this will give you the lower bound.
Okay, okay, nice.
Yeah.
Okay, and another question.
Yeah.
So what about 5 cycles? It seems like it's more symmetrical. Like, could you do something cursive?
Yeah. So 5 cycles, I know how to get update time order n using the same idea we had. In terms of number of edges, I don't know what we can get there. Like I think we can get linear time there, but yeah, like I don't know how to get anything better for 5 cycles. And
It just feels like it's more symmetrical, and maybe you can
right,
just
right, right.
recurse and that don't have to worry about high
Yeah,
and low and things like that.
right, right. The thing is, in this reduction, so after you make the problem about paths instead of cycles, the 4 cycles case seems more symmetric because there are just like three matrices there. And for 4 cycles, there is probably one more. But yeah, I don't know. Yeah, maybe for 5 cycles, you can do something as well.
Okay,
Yeah.
thanks.
Thank you.
Very nice. Yeah, thanks.
Can you make it what? Uh, yeah, yeah. I mean, okay. What do you mean exactly? Like, so. Okay, good. So yeah, I think you should be able to make this parallel. The thing is, we're getting updates because so we're getting an improvement because we're using this fast matrix multiplication. But I don't know how to make the fast matrix multiplication part parallel, right? Like matrix multiplication, of course, you can make it parallel, but I don't know how these improvements you can make it parallel or not. Like, uh, like, like Starsons and things like. Okay, okay, good. So, okay.
Or actually, it's not. Even
I see.
what you want. Small. Is not. Just make it small. You don't want to use raw so long in the process. Not looking is good.
Uh-huh.
It's not big small.
Mm-hmm. Right. Mm-hmm. Yeah, and I think even if you go to the algorithm of previous work, like when you're updating these data structures and things like that, you can do those things in parallel as well, right? So I think even that can be made parallel, but I have not thought about it. Uh-huh. Right, right. I think so. Yeah.
It's not a good version. So, copy from this. It's a very easy.
Mm-hmm. Right. Yeah. Fair.
Yeah. Next, so look at is NPC.
Thank you so much, Alina. You're muted. Do you have a question?
No, no, sorry. Thanks. This was a very nice talk.
Thank you. Thank you.
Yeah. It's